Ladies and gentlemen, this class recording has started. So, section 6.2 gets us into, like the title says here, work and energy. And I always struggle a little bit with this section because, or this chapter, it's probably going to be loud in the recording, but that's going to be great on the recording right there. So, all right, so there's always something I struggle with in this section is because work and energy always come together in the same chapter. And how to introduce and describe work and energy is really kind of a chicken and an egg thing. Do I talk about work first and how it affects energy, but you don't really know what energy is, so it doesn't quite make sense. But if you talk about energy, then sometimes that doesn't make sense with work because you don't know. They're really kind of an interrelated concept. So we talked about work in section 6.1, and we talked about how we do work and the factors that affect work and how we calculate the amount of work, but not actually what work is. So that's what we get into here in section 6.2. And right underneath the heading, I have included these two statements which really go a long way to explaining how work and energy are related. So, first, when you do work on something, you change its energy. And that's going to be very important a little bit later on. But then, similarly, energy has the capacity to do work on an object. So now we've gone from, okay, I know what work is, and I know how to calculate work, but I don't really know what it is, to, okay, well, work changes energy, but now I don't know what energy is. And so, before we go any further, let's talk about energy. This is my definition of energy that I like to use and I think is very descriptive, and I will use from now until the end of the year because it comes up a lot over and over and over again in a lot of different applications. So, energy. And this isn't necessarily the definition from your book or any book necessarily. I've kind of put it together over the years and kind of modified it a little bit, but this is how I like to explain it. All right, so energy. The ability to move or change other objects. Like I said, that definition will carry us pretty much from now until the end of the year because energy shows up in a lot of different applications, a lot of different instances, but it will always come back to this definition. And if we then use it in our description of work, like, oh, well, if work is the ability to change energy or work changes energy, you change its ability to do stuff based on what you've done to it. Okay? So, with that in mind, let's start with a type of energy that I think most of you have heard of before and talked about a little bit, and that's kinetic energy. And, there it is. Like it says up in the heading, right, kinetic energy is the energy of motion, or energy due to its motion. By the fact that something is moving, it has the ability to move or change other objects. Okay? So, yellow demonstration ball, right? Moving through the air, knocks over my water bottle, right? And messes some papers up and things like that. It only does that, though, when it's moving. Now that it's sitting on the ground not doing anything, it doesn't have the ability to move or change stuff anymore. The fact that it's moving gives it that ability. nowhere close to the board in that case. So only by virtue of its motion does it have that ability to move or change other objects. There are two factors that affect the amount of kinetic energy something has. That object's mass and its velocity. And as you can see down here at the bottom, key point, kinetic energy increases linearly with the mass, but it increases with the square of the velocity. And that's reflected by the formula, right? Ke equals 1/2 mv squared, where m, right, direct relationship with kinetic energy, but the velocity has a quadratic relationship with kinetic energy. For example, so let's say, because it's the holiday season. I really hope this is working, by the way, because I didn't unplug it and plug it back in, but whatever. So, it's the holiday season, so you go to Crocker Park to do some shopping. Okay? And you're in the parking garage. You're coming back down. You found the perfect gift for whoever it might be, that special somebody. Right? And you're coming around the corner, and you accidentally tap the fender of another car that's parked there. Okay? What? Yeah, they're not really. So, like, for any particular reason, or just? Yeah. So, you're in the parking garage, so you're only going 10 miles per hour. And, right, okay, so there's a little damage to the fender of the car that you ran into, right? You should stop and you should, notify the security so a report can be filed and stuff like that, but that's story for a different day. Yeah. So you finish up that, and then you finish going out of the parking garage, okay? And now you're driving through Crocker Park, looking at all the fabulous holiday decorations, right? You come around the circle, and you're looking at the big tree, and you're going a little faster now, 20 miles per hour, okay? But you didn't see, I don't know, like, do they have those little bike ride things that, like, maybe there's, what? Pedicab? Yeah, like something like that, right? And it's sitting still, right? Or the train, right? Or maybe another parked car, just so we're consistent with our demonstration, okay? I know, this story sounds really bad for you guys, by the way, just your driving talents, okay? So let's say you're going 20 miles per hour now, and you hit another parked car. Yeah, well, that's going to be the moral of the story, actually, eventually. So, all right. So you're going twice as fast, and you're going to do damage to the other car. But if we look at the equation, right, it says the kinetic energy increases with the square of the velocity. Meaning that if you go from 10 to 20, you're going twice as fast, but your ability to change other objects isn't twice as big, it's 4 times as big. Because 2 squared is 4. So now you've done damage to another car, not twice as much damage, but 4 times as much damage. Okay? Because your energy increases with the square of your velocity. So, you file another report, okay? You know that you're just going to be in serious trouble when you get home, so you head home, right? You're driving through your neighborhood, okay? 30 miles per hour now, right? But someone's got an awesome Rudolph and Santa thing going on, so you're looking at that. Little did you know, you did not see the parked car in the street in front of you. So now you've hit your third parked car in a matter of 45 minutes, okay? This time going 30 miles per hour, all right? In the parking garage, you were going 10, little fender bender, right? Inside Crocker Park, you're going 20, not twice as bad of a crash, but 4 times as bad of a crash. Now you're going in 30 miles per hour in your development. How bad of a crash? 9 times as bad as the original fender bender, right? Because 3 squared is 9, right? So, moral of the story, right? 1, don't run into 3 parked cars in the matter of an hour, okay? 2, slow down, because the faster you go, right, your kinetic energy increases not just linearly, but with the square of that velocity, right? If you're going 40 miles per hour, right, well, let's jump it up, right? If you're going 70 miles per hour on the highway, right, how bad is your highway crash versus your fender bender in the parking garage? It's 49 times as bad, right? Because 7 squared is 49. Okay, it's bad. That's why even even if you increase your speed from 60 to 75, right? Yeah, you're not doubling it. It's not 4 times as much, but because the velocity is squared in that formula, that damage really starts adding up, right? That's why cops always tell you slow down, or in driving school, right? And they're like, that kind of stuff. Nice. What are you trying to say? You saying a driving instructor could teach this class? So tell me. So. Next chapter. Nice. So. Yeah. So next chapter we'll do collisions. So talk about that. That'll be a good time. So. All right. So down at the bottom of the front page, we have a quick example 6.5. I will spare you from having to go through this step by step with me. I'll just write it up on the board, right? So here we are, right? Oh, sorry. So for part A, what is the kinetic energy, right? That's our unknown. The mass of this object, 3,900 kilograms, moving at 6 meters per second. That's the velocity. We just learned that the formula to determine the kinetic energy of an object, 1/2 mv squared, right? We plug in what we know. 1/2 is a constant, that doesn't change. 3,900 kilograms, 6.0 meters per second, okay? So we do the math, and if I remember correctly, we get 70,200. So, a couple of things before we wrap this up. First, units, right? The kilogram goes here, right? But then the unit for velocity, but mathematically we're squaring velocity in that formula, so we have to square the unit as well. So you end up with meters squared over seconds squared. You put those two together, you get kilograms times meters squared over seconds squared. Hopefully you remember from the last section, but in case you don't, that combination of base units we represent with the joule. Okay? So that's how we see here that kinetic energy has the same unit as work. There's a reason for that. We'll see it in just a second. Okay? All right. Good there with part A. For part B, what is the Chuck's kinetic energy if speed is doubled to 12 meters per second? Now, you could just plug 12 back into the formula, or you could make use of the fact of what we just talked about. In going from 6 meters per second to 12 meters per second, what have we done with our velocity? Doubled it, right? So, for part B, we went from V to 2V, right? That's doubling the velocity. That means what's going to happen to our kinetic energy? How much bigger will it be? 4 times as big, right? So we go from KE to 4ke. So we just multiply our answer from the last problem by 4, and you should get 280,800. Sorry. And that's going to be joules as well, because that is 4 times our answer from the previous problem. Okay? Good there. Questions? Okay. The next section gets into the relationship between work and kinetic energy, which is really an important part of this section. This picture, similar to the picture that we introduced back in section 6.1 on work. We have an object, right, this box, a force is being applied to it. That object moves because of the force. Now, we've simplified it a little bit here because we have put this object on an ice rink. And let's say, for the sake of argument, just to make our lives easier, that ice rink is completely frictionless. If this lady is pushing the box on a frictionless ice rink, what will it do? Yes, that will happen. While the force is being applied, what will happen to this box? It'll keep moving after she lets it go because of inertia. But while she's pushing it, right, it accelerates, right? If there's no frictional force holding it back, it will accelerate. And so, it goes from some initial velocity vi to some final velocity vf. And that happens over the course of some distance because of this force that we have applied. So now we start putting pieces together of topics that we have discussed previously. The next page gives you a derivation of an equation. I will not hold you responsible for deriving this equation. You only need to know how to use it at the end. But I want you to see where it comes from. Okay? So, let's take a look. That equation right there is one of our kinematic equations that we learned in chapter 3. It relates the final velocity of an object, the initial velocity of an object, its acceleration, and the distance traveled during its acceleration. Okay? It's one of those ones in table 3.3, I think it was, and it's on page 88 of your book, whatever. We use them to relate the different things that we use to measure motion. It's a kinematic equation. Okay? And then, just doing a little subtraction, you can turn the first equation into the second equation. Good there? Okay? Now, in the last chapter, we introduced the idea of what factors affect the acceleration of an object. And those factors are force and mass. Newton's second law gives us that expression. Okay? Taking this and putting them together, we end up with this. Does that make sense? How I got to that? Okay. Now, over on the left-hand side, look, we have a force and we have a distance. And we talked about that force and distance are the two factors that affect the amount of work that's done on an object. There's a couple other things over there. So, like it says, we just replaced A with F over M. Okay, that's what gave us this equation. Then, if we take this side of the equation and multiply it by m over 2. These 2's will cancel, these m's will cancel, and the only thing that's left on the left-hand side of the equation is F times D. But if you multiply one side of an equation by something, you have to multiply the other side of the equation by that same thing, right? We distribute it out, and we end up with that equation right there. Okay? FD is equal to 1/2 mvf squared minus 1/2 mvi squared. See how it came? Did you see how we got there? Did I lay it out okay for you? We know that F times D are the two factors that affect the work of an object. So that shows up here. And then we keep the other side of the equation the same, and we end up with this equation. Now, you have a VF squared minus VI squared. When we talk about the change in something, or the delta function, right, it's always final minus initial. So, this term right here, 1/2 mvf squared, we just learned that that's the formula for kinetic energy, right? 1/2 mv squared, but specifically, that's the final kinetic energy, because we're using the final velocity of that object. Yes? And then this specifically would be the initial kinetic energy, meaning that the left-hand side of that equation, or sorry, the right-hand side of the equation, we could replace with delta KE. Yes, no, maybe. That all make sense? So we end up with work equals delta KE. And we refer to that expression as the work energy theorem. The total work done on an object equals the change in its kinetic energy. So we said the very first thing that I had you highlight on this page, right? Work is equal to the change in energy. It's the very first thing on the first side of this packet, right? And here, we see that represented mathematically, that work is equal to the change in the kinetic energy. So by doing work on an object, applying a force, moving at a certain distance, we change its ability to change other stuff, right? Yellow demonstration ball can't do anything to anything else until I do work on it, until I apply a force and move it a certain distance, because I change its kinetic energy, and that then changes its ability to do other things. Good there. Okay, tomorrow we will start applying this to some different situations, do some calculations, talk about applications of it, and then hopefully by the end of the period, we'll see how this leads into potential energy and what that means. Okay? Oh, there is some homework on the calendar. Goes along with the kinetic energy stuff that we talked about. You should be able to do most of it, but if not, we can save it for tomorrow as well. Okay?